Hey everyone, in this video we're going to briefly summarize how and why ionic bonds form and go through the rules for writing the names and formulas for ionic compounds. We're going to focus on ionic compounds containing only main group elements in this video. So let's get started. So in summary, ionic bonds occur between metal ions and non-metal ions. The metal loses its valence electrons to a nonmetal, so the electrons are transferred from the metal to the nonmetal. The metal then becomes a positively charged cation, and the nonmetal becomes a negatively charged anion. The transfer of electrons then results in the two oppositely charged particles, which will be attracted to each other and stick together to form the compound. They stick together in this crystal lattice structure. Okay, that's this structure right here. And that we can see is in a solid state. Okay, we call it a crystal lattice just because we can see kind of this specific pattern that these ions will form when they arrange themselves so that they're surrounded by the oppositely charged piece, right? You can see chlorine is only touching the positively charged sodium ions there. We also need to note that even though ionic compounds contain charged pieces, the compound itself will have an overall charge of 0. The positives and the negatives will always balance each other out to have a neutral compound overall. So here's an animation of how this works, right? We can see that yellow electron being transferred from the sodium atom to the chlorine atom. That leaves the sodium positive. The chlorine now has that extra negatively charged electron, giving it a negative charge. And then they are sticking together with that electrostatic attraction. So how many electrons will participate in this transfer? It's all based on valence electrons and that octet rule we keep hearing about. Atoms want to look like a noble gas and have a full valence shell of electrons. That generally means having 8 valence electrons. The nonmetals that live over here in yellow already have pretty close to 8 valence electrons. Most of them have 5, 6, or 7 valence electrons. So they only need to gain a couple more to match that electron configuration of the nearby noble gas. Metals, on the other hand, are far away. Okay, we're going to be mainly talking about these metals and these metals here, talking about the metals in the tall groups, the main groups. So they only have 1, 2, maybe 3 valence electrons. So rather than gaining 6 or 7, they'll just lose a couple to resemble the noble gas at the end of the row above them. Also recall that we talked about metals reacting by losing their electrons and having low ionization energy values, meaning it's easy for them to lose electrons. And then nonmetals are the opposite, right? They react by gaining electrons. They have those high electronegativity values. And so these kind of guidelines here match those same periodic trends that we have talked about previously. So you're definitely going to want to label your periodic table with the different charges that elements will take on. So I just kind of explained why these specific elements take on these charges. And so hopefully understanding that will allow you to remember. But also, please just do label your periodic table. Everything in group 1 is going to lose its 1 valence electron to look like the noble gas before it. Sodium is going to have 11 electrons in a neutral atom. It's going to lose its 1 to have 10 to match neon, right? So it's always going to be a +1 charge. Everything in group 2, always going to be +2. Okay, we see aluminum and gallium always having +3. We kind of skip this column right here. Some people will write plus or -4. You can write that. We generally just don't really use those elements in ionic compounds, and if we do, they have a different set of rules that we'll talk about. Then we have nitrogen and phosphorus with a -3, oxygen, sulfur, and selenium -2, the halogens -1, and then obviously our noble gases, they already have their full valence shells, so they will not form ionic bonds. They have a charge of 0. Okay. Also, pay attention to these specific elements in this shaded area. So this shaded area, for the most part, are our transition metals. Okay. However, silver and zinc, cadmium also, but we don't really see cadmium as much. Silver and zinc are the ones you definitely want to remember. Silver is always going to have a +1 charge, and zinc is always going to have a +2 charge. So now that we've labeled our periodic table with these charges, we're going to use this information to be able to write appropriate and correct ionic formulas when we are given the name of an ionic compound. So when we're given the name of a compound, we first need to determine if it's ionic or covalent. We're going to do that by looking at the types of elements that are represented in that name. So the example we're going to work through here is sodium nitride. Okay, that's sodium and nitrogen. So sodium is here, nitrogen is here. So we know we have a metal and a nonmetal, which means we're dealing with an ionic compound. So that's how we know these are the rules we're going to follow. So our first step is to determine the charges of the cation and anion by looking at the periodic table, specifically your labeled periodic table that you just labeled. So working through the example step by step, sodium is Na, and it lives in group 1, so we can see that that group is labeled with a +1 charge. I like to write this out. This is essentially showing my work here, and then I will circle my final answer when I'm done, so you can see what a final formula should look like. Okay, then so sodium's +1. I circled nitrogen over here. It is in group 5. It has that -3 charge. Sometimes you might see and them written with sodium as just a plus or nitrogen with a 3-. Either of those are fine. I like to write the charge first, then the numerical value, even if it's a 1. You might see them the other way though, just as a heads up. All right. Step 2 is to determine how many, okay, also known as the ratio of each ion are needed to make a neutral compound. So we need to make sure that the charges, the positives and the negatives, balance each other out to make a neutral compound overall. So these numbers, so however many of each piece I need to make these neutral compounds, will be the subscripts. So let's work on that for this example, sodium nitride. So right now I can see that sodium has a +1, nitrogen has a -3. A +1 is not going to even out a -3. I'm definitely going to need some more positives. So if I add another sodium, now I have a total of +2, right? If I were to tally my charges here at the bottom, they're still not even, so I'm going to need a third sodium to even that out. So now I would have 3 +1s for a total of +3, and that will cancel out my -3. So what that means is I need 3 sodium ions to even out my nitrogen ion. So this is my final formula. Okay, please note that in this formula, there are no positives, no negatives, no charges written out. It is simply the ratio of how many sodium ions I needed to even out that negatively charged nitrogen ion. Okay, another way we can think about this is we can think about making sure the charges match the least common multiple of both of them. So if I think about +1 and -3, well, the least common multiple of 1 and 3 is 3. So I need my positive charges to match 3, and I need my negative charges to match 3. In order for the positives to match 3, I need 3 sodiums. In order for the negative charges to match that least common multiple of 3, I only needed 1 nitrogen. Okay, so the formula for sodium nitride then is Na3. N. Let's do some more examples. Lithium bromide. So I'm going to find lithium on the periodic table. I'm going to show my work the same way. It lives in group 1 with sodium, so it has a +1. Bromine lives in group 7. It has a -1. Well, +1 and -1 seem to even each other out pretty easily. So that means this formula then is just going to be LiBr. The least common multiple of 1 and 1 is 1, so I only need 1 of each of those. Okay, moving down here, we'll go in a different color. Magnesium phosphide. So magnesium, Mg, we find it on the periodic table, lives in group 2, so it has a +2. Phosphide is referring to the element phosphorus. Phosphorus lives in group 5, so it has a -3 charge. Well, this one seems a little tricky. I have a 2 and a 3, and how do I balance those out? This is a great one to use that least common multiple trick. The least common multiple of 2 and 3 is 6. So I need a total of +6, and I need a total of -6. That's the simplest way for those to balance out. Well, to get a total of +6, I'm going to need 3 magnesium +2s. To get a total of -6, I'm going to need 2 phosphorus -3s. So my formula then, if I count those up, right, 1, 2, 3 magnesiums and 2 phosphide ions. So Mg3P2. Next example, calcium oxide. Find calcium. It lives in group 2, so it's got a +2. Find oxygen. It lives in group 6. It has a -2 charge. Calcium and oxygen even each other out in a 1-to-1 ratio. Each +2 is going to cancel out the -2. So when those charges match numerically, we can just mush it together and write our formula. Okay. We can also think about the least common multiple of 2 and 2 is 2. And so we do not need those charges to even out. We don't need any more of them. They will just cancel out. And lastly, silver chloride. Well, silver is not in one of those main groups, but it is an element that we labeled on our periodic table as always having a +1 charge. Then we find chlorine. Okay, and chlorine's got a -1, so again, those charges match. A +1 is going to even out a -1, and so that's just going to be AgCl. All right, so now we can go the other way. So if we're given the formula for an ionic compound, again, we're identifying those elements as a metal and a nonmetal. How do we name it? Well, the system is very different from the covalent compound system. We don't use any prefixes. This system assumes that you know that the ions are going to combine in the most reduced ratio possible to make sure it's neutral. Okay, the system assumes that you can use that labeled periodic table and figure out how many of each ion is necessary in that formula. So all we have to do is name the two pieces here. The metal's name always stays the same, so we just name the metal from the periodic table. And then we name the nonmetal, okay? So the nonmetal's name ending in "ide." Okay, metal name from the periodic table plus the nonmetal's name ending in "ide." Okay. I think this is just supposed to say ion here. We can also call this the cation name plus the anion name. Sometimes people will refer to the anion always just having that "ide" name, so like the anion name of oxygen just being oxide, for example. Okay, but again, no prefixes. You should never have prefixes on your ionic compound names. So let's try some examples. So MgO, okay, the metal there is magnesium. The nonmetal is oxygen. Oh, this is actually, I'm silly. This should be root, right? We use the root name. So the root of oxygen is really just ox, and then we change that ending to "ide." So magnesium oxide, okay? Next example, NaBr, the metal is sodium, so we just take that name right off the periodic table. Its partner is bromine. They're chemically bonded, so instead of bromine, we're going to change it to bromide, so sodium bromide. Then going over to the right side here, strontium is Sr. So again, we take that right off the periodic table. And that nonmetal here is chlorine. Okay? It doesn't matter that there are two of them. That's the ratio these ions are going to combine in. All we need to do is name the two ions. So strontium chloride. That's it. No di, no prefix, just strontium chloride. Okay, that formula is always going to look that way because strontium always has that +2 and chlorine always has that -1. So that ratio is always going to look that in that format. Okay, and same thing here. Ca and N. Doesn't matter how many of each of them I have, just that they are those ions. So calcium is Ca, N is nitrogen. We're going to take that root nitride. So calcium nitride. Okay, so in a sense, it's simpler because you're just naming the pieces. You're ignoring the subscripts for the most part. So just name the metal right off the periodic table, the nonmetal from the periodic table, but change the ending to "ide." Marry them together. So ionic compounds can also contain those transition metals we saw in that purple shaded area on the diagram earlier. And they can also contain things called polyatomic ions. But I'm going to do separate videos on those just because they are a little bit different. So those will be coming up and you'll want to watch those next.